Singularities aren't about infinite anything. This is a common misconception, so let's clear it up. If you're interested in space or physics at all, surely you've heard of black holes or the Big Bang. And if you've watched Neil deGrasse Tyson or others, you would have perhaps reasonably believed that when a physicist says there's a singularity in spacetime, they mean something like the matter density is infinite there, or perhaps more sophisticatedly, that a scalar curvature invariant diverges there. And while this understanding of a singularity hits a lot of prominent examples, it misses others and gets non-singular spacetimes wrong. What a singularity really is somewhere, or somewhen, that is a dead end for at least one path through spacetime that runs into it. The technical phrase is geodesically incomplete. Essentially, if you are traveling along one of these paths, you get stuck in space and time when you get there. In other words, you cease to exist. You have no future, nowhere to go. In my view, this is a pretty good definition, and if you don't like it, you can blame Roger Penrose and Stephen Hawking. They were the ones, in their singularity theorems, that used it. In the case of Penrose, it was for black holes, and for Hawking, it was for the Big Bang. In fact, in Penrose's original theorem, for which he won the Nobel Prize, he showed that under sufficiently reasonable starting conditions, a singularity will inevitably form. But by singularity, he meant it in the geodesically incomplete sense. Nowhere in his proof does any notion of infinity show up. In fact, it was this exact confusion that led Kerr to write his paper claiming that black holes don't have singularities. Now, I mentioned that the infinity definition sometimes gives false positives and negatives for true singularities. As an example, consider a space-time cone, where moving around the cone is space and up the cone is time. If you remove the tip of the cone, then there is a trajectory, in fact many trajectories, that leads to a dead end, just sitting still and going up the cone. Eventually you reach near the top, and because the tip has been removed, you can't keep going. So your timeline ends. This is called a conical singularity, but strangely, nothing is infinite here. The curvature, in a technical sense, is zero everywhere on the cone, so nothing can become infinite. Alternatively, a thin spherical shell with infinite density but finite mass would have an infinite value for various curvature invariants. But because the mass is finite, nothing actually goes wrong for any trajectories. They can all pass through the shell no problem, no dead ends. That said, most of the singularities you might imagine have both. The center of a non-rotating black hole has infinite curvature and it's a dead end. The same is true for the Big Bang. So you weren't very wrong, just caught on a technicality.